Um, so hi, everybody, and welcome to today's Quantum Colloquium. So today it's a real pleasure to have Henry Yuen here. Henry was got his PhD from MIT. He spent some time in Berkeley as a postdoc, then as on the faculty at University of Toronto, and he's now on his way to Columbia University. So Henry was involved in work on randomness certification, and then on this really celebrated work on MIP star equal to RE, which really looking forward to hearing about. So Henry, please.
Cool. Thanks, Umesh. Yeah, and thanks for the invitation to speak at this colloquium. So today I'm going to talk about MIP star equals RE, which some of you have heard about. This is a theorem that was proved last year with my amazing collaborators, Jianfeng Ji, Anand Natarajan, Toma Vidic, and John Wright. And one of the things that makes this theorem very interesting is that there are many angles from which to understand it. And in this talk, I'm going to discuss it through one particular lens, which is that of proofs and proof checking. So let me just dive into it. I'll start by defining what MIP star is. This refers to a model of multiprover interactive proofs with entangled provers. In this model, there's a classical polynomial time verifier that interacts with two computationally unbounded provers. These provers are not allowed to communicate with each other during the interaction, but they're allowed to share quantum entanglement to correlate their messages that they send back to this verifier. So that's the model. And MIP star, it's a complexity class, and it consists of all decision problems that admit an interactive proof in this model. So the verifier gets some input X, and in order to determine whether the input is in the language or not, the verifier interacts with the provers. And at the end, if X really is in this language, then there exists a strategy for these provers. They choose some quantum entangled state to share, and they have a set of measurements that they perform on the entangled state, such that the verifier accepts the interaction with high probability. But on the other hand, if X is not in the language, then no matter what strategy the provers use, the verifier will reject with high probability. So this is a model that was first introduced by Cleve, Hoyer, Toner, and Watrous back in 2004. So that's MIP star. Now, what is RE? So RE stands for the set of recursively enumerable decision problems. And this complexity class is absolutely enormous. It really should be called, it's a computability class, really. And it contains P, NP, exponential time, doubly exponential time, you name it. It contains all decidable problems, and then some. So the complete problem for RE is the halting problem. And this is to determine which Turing machines eventually halt. And famously, Turing showed that the halting problem is undecidable. So there's no algorithm to actually solve this problem. So RE is, it's an enormous class, contains lots of very difficult problems. And this equality between MIP star and RE gives a characterization of the complexity of entangled prover interactive proofs. So every problem that can be decided by an MIP star protocol can be reduced to the halting problem. This is not so hard to show. But the reverse direction is also true, which that every problem in RE has an MIP star protocol that decides it, including the halting problem. So there's a number of surprising and unexpected consequences of this equality. One of them is, there's no algorithm to approximate the maximum success probability of non-local games. That's one. There's another consequence, which is this equality gives a negative answer to something known as Sirelson's problem from mathematical physics. I won't describe this. It also gives a negative answer in turn to something known as the Kahn embedding problem from operator algebras in pure mathematics. Like I mentioned, it means that there is an interactive proof for the halting problem in this model of entangled provers. So this talk is going to focus on this last one. So I want to sort of explore what does it mean to have an interactive proof for an undecidable problem? How is that even possible? Okay, so what does it mean? So in this MIP star protocol, the verifier is going to get as input a description of a Turing machine. So think of it as the source code of some computer program. And the provers here, we're assuming that they're computationally omniscient. They can solve undecidable problems in one step. So they know whether M halts or not. But what the verifier wants to, the verifier also wants to know whether M halts or not. And it wants to know if I took this Turing machine and I ran it, would it eventually stop? But the problem, of course, is that this Turing machine might take an enormous number of steps to run, far beyond whatever time the verifier has. And so the verifier wants to enlist the help of these provers to become convinced of whether it halts. So it engages in this interactive protocol. The provers will make use of their quantum entanglement to decide what messages to send back to the verifier. And if M does eventually halt, then there is an entangled prover strategy where the verifier will actually accept with probability 1. But if M never halts, then no matter what the provers say, the probability that the verifier accepts is at most, let's say 1%. This constant can be made arbitrarily small, but the important thing is that it's bounded away from 1. So what's really remarkable is that the complexity of the verifier, how much time it takes to run this protocol, it's polynomial in the description length of this Turing machine, but it's independent of the running time of the Turing machine. Okay, so this Turing machine could take 10 lifetimes of the universe to eventually halt, but this doesn't matter for the protocol. All that matters is actually how many bits does it take to describe the Turing machine. And at the end of this interaction, the verifier may still have no idea what's even a reasonable upper bound on how long it takes for this Turing machine to halt, if it does eventually halt. Okay, so when I talk to people about this result, I've often encountered this question of whether does this mean quantum computers can solve the halting problem? So I want to emphasize that this result does not imply that. We know that quantum computers cannot solve undecidable problems. Classical computers can simulate quantum computers with at most an exponential slowdown. MIP star equals RE is not about solving the halting problem, but instead it's about efficient verifiability of it. So, again, these provers are omniscient, they can solve any problem they like, but, the challenge for them is for them to convince a computationally limited verifier of the correct answer. So, still it's pretty counterintuitive that in this MIP star model, which is pretty well motivated and it's a pretty reasonably defined model of interactive proofs, that unsolvable problems like the halting problem can be verified. This talk is going to explore how this is possible, and my goal today is to try to shed some light on the following questions. How can there be an interactive proof for an undecidable problem? How do proofs and proof checking play what role do they play in MIP star equals RE? Where does quantum come in? Why is this entanglement useful? Hopefully I'll try to give some answers to that. And towards the end, if I have some time, I'd like to describe some questions in an area that I call non-commutative property testing. And these these questions are motivated by the phenomena that occurs within the techniques and tools that are used inside MIP star equals RE. Okay, so let's get into how do you prove that a Turing machine eventually halts? So I want to consider a slightly easier version of the halting problem. This is called the bounded halting problem. So here, imagine that someone walks up to you and they claim that a Turing machine M halts in a time t. So they're going to give you a specific time bound for you to check. How do you verify this claim? Well, this someone could just provide you with an execution trace of M. So this would be a step-by-step record of all the computations that M takes. And you can verify this by just scanning through each of the steps line by line, and you verify that it's a valid execution trace. But of course, this takes at least time t to verify, and you might as well just run the Turing machine yourself. So this doesn't seem like a very efficient way of checking. But if you allow your verification process to be randomized, then it's possible for someone to provide what's called a probabilistically checkable proof, or a PCP, of the fact that M halts in time t, if that is really the case. And the time to verify a PCP can be much smaller than this original time t. It can be polylogarithmic in t, so an amount that's exponentially smaller than the original time bound. So here's the setup of a PCP. It's some string of length poly t. And we have a verifier here that runs in time polylogarithmic in t. And the verifier will choose random locations in this proof to sample and check. So the verifier will select random queries q1 up to qk, and it receives proof symbols from this long string, say pi q1 up to pi qk. And the verifier, based on its queries and the proof symbols that it receives, it'll compute some function and decide whether to accept or reject. And in the context of this bounded halting problem, if M halts in time t, then there is such a proof string of polynomial in t length that this verifier will accept with probability 1. But on the other hand, if the claim is false, then no matter what proof string you write down, the verifier will accept with, let's say, at most 1% probability. So this is quite a remarkable fact that you can check these really long computations using an extremely efficient verifier that doesn't even have enough time to read in the whole proof.
Henry, are you assuming multiple provers here?
Oh, so here I'm talking about PCP. So the proof here is just a string. But I'm going to connect it to the prover setting like in the next slide.
Oh, okay. So you have an exponentially long proof string. Okay.
That's right. Yeah.
Fine.
Yeah. Yeah. The proof string is exponentially long in the running time of the verifier. Yeah. So, so Scott brings up a good question. Before I was talking about, a verifier interacting with different provers, and now I'm talking about verifier looking at bits from a long string. What's the connection? Well, the connection is going to be as follows. So, the existence of this PCP for this bounded halting problem with this very efficient verification, this is a consequence of, I guess that you could say it's the classical precursor of MIP star equals RE. This is MIP equals NX. And this was proved nearly 30 years ago by Babai, Fortnow, and Lund. And so MIP without the star, this is multiprover interactive proofs with deterministic provers or classical provers. Okay, so in this talk, they'll be designated as not having squiggly lines between the provers. So it means that they're classical. And NX is a complexity class. It stands for non-deterministic exponential time. And it essentially corresponds to exponential size NP problems. And it turns out that these two complexity classes are equal. And right, so there's somehow two different models of proof checking that I've introduced here. One is this interactive proof, and one is where a verifier is just reading bits from a very long string. So how do we connect the two? Well, let's say you had a PCP verifier. So this is the verifier. Well, it looks at queries, locations in this very long string. We can convert it to an equivalent MIP verifier with equivalent complexity. So here's how the transformation works. So what V prime is going to do, V prime is this verifier in this interactive proof. It's going to run the PCP verifier to generate queries Q1 up to QK, as if there was a long string out there, but instead it has provers to talk to. So V prime is going to send all of the queries, these PCP queries, Q1 up to QK, to the first prover. And it's going to get some answers, A1 up to AK back. Okay. And the thing to note here is that since we're in this interactive setting, there's no guarantee that this A1 up to AK corresponds to bits of a proof string. Okay. To the second prover, the verifier is going to choose one of the queries QI at random, okay, from this list and send it to the second prover. Okay. And it's going to receive some answer B. And the important thing here is that the second prover has no idea what is the collection of queries, Q1 up to QK. It only sees the ith one. And once the verifier gets all the answers back, it's going to check, would the PCP verifier have accepted the answers of the first prover according to these queries, okay? And it's going to check that the second prover's answer is consistent with the first one. And the effect of all of this is that, you can think of it in the following way. This first prover, again, he only sees a single query at a time. And since we're imagining that these provers are deterministic, you can imagine that all of the responses of the second prover form a proof string pi. Okay, and because we're doing a consistency check between prover 1 and prover 2, we're essentially prover 1 has to just respond honestly with bits from this proof string pi. It cannot change its answer depending on what collection of queries it gets. So, through this transformation, you can argue that this resulting MIP protocol is equivalent to the original PCP protocol. And if there was a proof string pi that was accepted by this top verifier V, then there's some prover strategy that's also accepted by V prime, right? They just take that proof string and just reply honestly from it. And if all proofs pi are rejected by this PCP verifier with high probability, then you can also argue that no matter what the provers say, they get rejected with some at least 1 over k probability, which can be amplified to nearly 1 by repeating not too many times. Okay, so the upshot of this is that given, if you know that there's a PCP for this bounded halting problem, there's also an MIP protocol for it. And here the verifier complexity still must depend on the complexity of M. There's, the verifier's runtime is polylogarithmic in T. Right? But remember, our eventual goal is to somehow get this verifier complexity to be independent of T. So how do we get there? And this is, we're going to have to use entanglement somehow. So, let's imagine the following situation. Let's go back to the PCP setting. So we have a poly T length proof, PCP proof pi. Okay, so it's very, very long. And we have a verifier that runs in not just logarithmic time, but log time. So it's this proof string is going to be doubly exponentially long in the complexity of this mini verifier. So here's some wishful thinking. Can we somehow get this log t complexity verifier to check a proof of poly t length? Okay, so it's not going to be able to do it by itself, not without some help. And one of the barriers is that the randomness of this verifier, since it runs in log t time, it only has access to log t bits of randomness. So how many different locations of this proof could it individually address? It's at most logarithmic in t, and that's still a vanishingly small fraction of this entire proof. So it couldn't even flip enough coins to refer to every location in this proof. So that's a problem. So you can't do this directly. But what we do know is that there is a log of t complexity verifier. So not a mini verifier, but the original verifier that we just talked about, that can check this large proof. So why don't we imagine just replacing this? We somehow encode the verification procedure of this, say, medium-sized verifier into a PCP proof pi prime. Okay, and what this smaller proof will verify is that the original verifier V, if it made these PCP queries using polylog t randomness, and if it checked this proof, that it would have accepted on these queries and these proof bits. So if we had such a proof, then this mini verifier could, using log t time, just verify the validity of this proof, and thereby actually check the correctness of this larger proof via proxy. So, in order for this scheme to work, we need to assume that we need a couple assumptions to be satisfied. One is that this randomness Q1 up to QK that's fed into this this intermediate verifier is actually random. Okay, it's actually polylog t bits of randomness. And this proof, this smaller proof, when it gets this these queries and it performs some computation on these proof bits, that it's actually consistent with the larger top level proof up here. Okay, but if these two assumptions are satisfied, then this mini verifier can, like I said, it can check the validity of this top proof pi just by checking this smaller proof pi prime, which is only of length polylog t.
Okay. Henry, when you say random, do you mean like these are uniform and independent marginally? They're all the same?
Oh, good. So in reality, no, they're going to be correlated random bits. But for the purposes of this talk, I'm just going to assume that they're just uniform randomness. But of course, they have to be correlated in the right way. Yeah, good question. Okay, so I should mention that this idea of checking a much larger proof by verifying a verifier, this is the basic idea behind something known as PCP composition, and this was used in the proof of what's known as the PCP theorem. So this is not a new idea. What we want to do is to take this PCP composition where you just want to iterate this over and over again by, instead of having, say, a log t verifier V mini, why don't we just have another proof that certifies that this verifier would have accepted, this intermediate proof and so on. So you can imagine having an even smaller verifier V micro that checks, this third level proof and so on. Okay. So you can imagine iterating this scheme, and that's sort of the high level idea of what we want to do in MIP star equals RE. But again, we still have these assumptions that still need to be satisfied. One is that the queries at all these levels are actually chosen randomly, and as Madhu mentioned, they have to be chosen from the correct distribution. And you have to make sure that the proofs between all these different levels are consistent with each other, right? That this proof in the middle refers to proof symbols from the previous proof, and so on.
I'm sorry, Henry. So you could also have referred to just the randomness instead of the query locations, and then it would have been independent random bits. Is that correct? Or
so could you say?
Couldn't you also just have referred to the randomness that was used to determine the query locations? And then you wouldn't have to worry about the correlations at all. It would just have been independent random bits.
Sure, right. Yeah, that's right. Yeah.
Okay.
Yeah. The queries are a deterministic function of the randomness. Yeah. So that's right. You just have to make sure that that you really have a source of genuine random bits of large enough length. Okay, so these two assumptions, you have to make sure that they're satisfied, and really the main bottleneck actually is this certifying the randomness. So if we have this really tiny verifier at the very bottom, and maybe it runs in log t time, how can it verify that there's this original polylog length randomness? Okay, and classically, this is why you can't carry out this recursive proof composition endlessly in the classical setting, because it doesn't make sense to prove that any individual string is random. And there's a very famous Dilbert cartoon, maybe some of you have seen this before, that really illustrates this point, that given any string, how can you tell if it's random or not? There's no proof for it per se. And this is where the quantum entanglement comes in. And this is where it'll actually help us certify that there is a source of randomness. And using this, we can actually carry out this recursive proof composition. Okay. So this brings me to the next part of the talk, which I'll talk about something known as the quantum low degree test. This is an efficient MIP star protocol for certifying entanglement. Once you're able to certify the presence of large amounts of entanglement very efficiently, as a byproduct, you can certify the generation of large amounts of randomness. Once you have that, then you combine this with this, this cartoon picture of recursive composition of proofs. And putting it all together in a way that I won't describe in this particular talk, you get the MIP star protocol for the halting problem. Maybe let me stop for a couple seconds here. Are there any questions about what I just described?
Henry, like the first assumption you mentioned, that there is a larger proof that is consistent with the smaller proof. I mean, is that also going to rely on the entanglement between the provers?
That part isn't. I would say that isn't the. Let's see. I would view it as the entanglement. The critical point of the entanglement is to generate the randomness.
Sorry, okay. Isn't the first part of the proof just referring to a Turing machine? And so your proof is just a classical proof, and you do a PCP of it. So there's no entanglement involved.
You mean the top level proof?
Yeah.
Right. I guess so. At the end, when you have this two-prover protocol, we're imagining that the top level proof is really some string that's sitting in the provers' heads, and you just want to force them to faithfully pick out symbols from it and do computation on those symbols and report to you, after they do all the proof compositions, the result of the smallest proof which you actually have the ability to access.
But we won't need entanglement to certify the existence of such a global string that is, that the provers are answering according to.
So I guess you would need it, but you need it because you need to get the randomness in order to be able to certify that it exists.
Okay.
Yeah.
Henry, another question. Maybe this is so in classical PCPs, when we think about this picture that you've drawn, this cartoon, all the green stuff would have been work done by the verifiers.
Mm-hmm.
Is it a good abstraction to think in this current context that any randomness is coming from some source, but it's not work done by the verifier?
Right. That's right. So yeah, because in particular in this situation, we don't want the verifier to be. It doesn't have enough time to even process those green squares because they're too long. So we're imagining that it's coming from some other source.
But does this source has to be something that the prover does not know, right? It can't be just like, you couldn't use a public source of randomness or something. Because if the prover knew the values of the green squares, it could provide a counterfeit proof.
Oh, good. So you're saying that here, these blue boxes, the proofs, they cannot be right. They cannot be chosen in a way that depends on the randomness.
So if I understand correctly, you have to not only choose randomness, but it has to be generated such that the provers have no access to it, right?
Mm-hmm.
But you're also going to have the provers generate it for themselves?
Well, I guess the important thing is it's fine if the provers have it, but their responses cannot depend. The proofs must be fixed independent of the randomness.
Okay.
And you have to certify that.
Okay.
Okay. Good. So now, basically, we want to reduce it to this question of how do we certify large amounts of entanglement or randomness very efficiently, and this is brings us to the quantum loaded retest. So let's think about the following system of equations. So let's imagine we have 9 Boolean variables, pi1 up to pi9. They all are bits, and these variables have to satisfy the constraint that all rows and all columns must sum to 0 mod 2, except for the very last column, which should sum to 1. So that's why I've shaded it in green. So it's easy to see that this is an unsatisfiable system of equations, right? You can just sum up all the constraints and see that you get a contradiction. So there's no setting of zeros and ones to these pi i's that satisfy it. We can turn this into this system of equations into an MIP protocol. And this is also known as the magic square game. So how does this game work? Well, the verifier is going to pick a random equation. So there's 6 possible equations. There's 3 corresponding to the columns and 3 corresponding to the rows. So let's call that equation E. And then the verifier is going to pick from this equation a random variable. So let's imagine that the verifier picks let's say the green column. So this equation would be pi3 plus pi6 plus pi9 equals 1. And then a random variable from this would be, say, pi9. So to prover 1, the verifier will send an equation, and to prover 2, the verifier will just send this variable, let's say pi9. Prover 1 will respond with an assignment to all the variables in this equation, and prover 2 will respond with an assignment to just the variable it received. And the verifier will accept if the equation is satisfied by the first prover and the assignments are consistent between the 2 provers. So their claimed assignment for pi9 matches. So it's easy to see that classical provers, deterministic provers, also cannot win perfectly, because if they could, then this would imply a satisfying assignment to all of these variables. But one of the amazing things about quantum entanglement is that if the provers use an entangled state, they can actually win this game with probability 1. So what they can do is, before the game starts, they prepare 2 EPR pairs. So in total, they share 2 qubits of entanglement. And based on the questions that they get, they can measure polyobservables on their qubits to produce answers. And the polyobservables they measure can be, you can choose them from this arrangement. So these are measurements that the provers can perform. So for example, if the second prover gets this 9th square, it will measure the YY polyobservable on its 2 qubits. And it turns out that this strategy allows them to win with probability 1. And this is another way to prove Bell's theorem, which is this famous theorem for physics. And really the remarkable thing is that the provers can always win, even though there's no satisfying assignment underlying their responses.
Henry, Marius Jung has a nice question. In your randomness verification through entanglement, is it not destroyed when you measure it?
Yes. So if you play a single, you play this game once and you generate randomness, then afterwards the entanglement that was used to generate the randomness collapses and you can't use it again. That's right. Okay, so in this game, one observation is that a winning probability that's very close to 1, you can think of it as a proof that the prover responses are random. Or another way to put it is that this magic square game is an interactive proof for randomness generation. And why do we know this? Well, if the responses were not random, then that would mean that they were using a deterministic strategy. And we know that this can succeed with probability at most 8/9 or some value like that, right? It cannot win with probability 1. So winning with probability 1, they necessarily have to have responses with some entropy in it. And this insight has been very useful in quantum information theory. And it's led to, in particular, this field of device-independent cryptography, where you can actually use this idea to get untrusted quantum devices to generate certified random numbers, for example. But we can make an even stronger statement about this magic square game. Not only does winning with probability 1 imply that it's generating randomness, but in fact, if it's using a quantum strategy, then this quantum strategy must look like a very specific one. In particular, it has to be equivalent to this strategy where you use 2 EPR pairs and poly measurements. There's no other strategy that it could be using. And this phenomenon is known as rigidity of the magic square game. So you can view it as not just interactive proof for randomness, but interactive proof for particular quantum properties. So for example, if they win with probability 1, then prover 2's measurements corresponding to the variables pi1 and pi5, these observables must anti-commute. That's one deduction that you can learn from this interactive proof. And the number of qubits of entanglement that they use is at least 2. And since we have such a strong characterization of what states and measurements these provers are using, randomness certification is just a corollary. If they're using the strategy, then we just by calculation, you know that they're generating uniform randomness. Okay, so but by itself, this magic square game is not so useful for randomness testing, and that's because the verifier complexity and the randomness usage is commensurate with the amount of certified entanglement and randomness you're getting out, right? So how much randomness does it take to even play the magic square game? Well, you need at least at least 3 bits of randomness. But the amount of randomness that you're getting from the provers is 2 bits. So, you're not making up for the amount of randomness you're putting in. So what we would like is a more robust and more efficient test for entanglement. So what we want is an interactive proof that you can run, and it will certify T qubits of entanglement. And ideally, we would like the verifier complexity to be much, much smaller than T. Let's say polylog in T. So this is the efficiency property. And the robustness property is that any prover strategy that succeeds with probability 1 minus epsilon must be delta of epsilon close to having T qubits of entanglement. So it's not so difficult to design interactive proofs that satisfy just one of these properties. Like you can get efficient but not robust tests, or you could get robust but not efficient tests. The challenge is to really hit both requirements at the same time. And that's what the quantum low degree test accomplishes. It's a test for T qubits, and it has this polylog T verifier complexity. And the robustness, it depends on epsilon and T. Epsilon is how close you are to winning with probability 1. And it has a mild dependence on T. It's polylog T times some polynomial in epsilon. So what this means is you get non-trivial guarantees as long as epsilon is at most 1 over polylog T. So what is the quantum low degree test? I think the simplest way to explain it is that it's really something called the classical low degree test plus this magic square game that we just saw. What is the classical low degree test? Now, this is something that comes from classical complexity theory. It's an efficient and robust interactive proof that the prover's responses are consistent with a low degree polynomial. So at the core of this low degree test is the following question. Let's say that you're given some function defined on over some vector space over a finite field, so f to the m, and it maps points in this vector space to elements in the finite field. Let's say that you knew that this function, when restricted to these one-dimensional subspaces, agrees with a low degree polynomial. Okay. Let's say you know on most lines that it had this property. Does this imply that this function f overall is globally close to a multivariate low degree polynomial? That's the main question. And this low degree test has been a very important component of the MIP equals NX theorem, the PCP theorem, and this field of algebraic property testing. And people study this for many, many years. So how does the classical low degree test work? It's this interactive proof. Again, F is a finite field. And let's say D is some degree bound. Let's imagine that it's much, much smaller than the size of this finite field. What the verifier is going to do, it's going to pick a random point in this vector space, f to the m, and it's going to pick a random line through this point. It's going to send the line to one prover and a point to the other prover. So the first prover should respond with a univariate degree D polynomial G, and the idea is it should represent the restriction of this global function to this line. So that's what G is supposed to be. And the second prover is going to respond with just a value B. And this verifier is going to accept if B is equal to G evaluated at the point on this line. So in the case of classical provers, this second prover, all it gets is a single query in this vector space, and it responds deterministically. So you can think of its responses as being characterized by some function f, okay? F defined on this vector space. And the low degree test tells us that if these provers pass with high probability, then we can actually characterize how close this function f is from being a low degree polynomial. In fact, it's, depending on how well they pass this test, that's how close f must be to this polynomial, some polynomial p. And this is an extremely good test because it's efficient. How much time does it take to conduct this test? Well, it's going to be polynomial in the dimension of this vector space and the degree and log f. And this is exponentially smaller than the size of this object f that you're characterizing. I mean, remember, f is a function that's defined on f to the m points. And you don't have to examine this entire object at all the points in order to determine that it's globally close to a low degree polynomial. Okay, so that's the low degree test. Now, how do we turn it into this quantum low degree test? Well, the idea is that we essentially play the low degree test in two different bases. So this verifier now interacting with now entangled provers, it's going to say with probability 1/3, play the classical low degree test in the z basis. Okay, and the provers will know that they're playing in the z basis. Or it can play the classical low degree test in the x basis. And with some, the last probability, the verifier will relate these two bases together via this magic square game. So this is kind of a high-level sketch of how this quantum low degree test works. This is an efficient test. Here are the guarantees of it. Suppose the quantum provers pass this test with probability 1 minus epsilon. What can we say about the structure of their strategy? Well, the state that they share must be close to 2 to the m EPR pairs. And their measurements must be close to collections of poly X and poly Z observables on this state.
I'm confused about something. If you're just trying to verify that the provers have 2 to the m EPR pairs, then isn't the polynomial just a constant polynomial? Like, what is the polynomial that you're trying to force the provers to answer consistently with?
Okay, so right. So let's say that they're playing the classical. Let's say they're playing the classical low degree test in the z basis. Then what they're supposed to do is measure all of their EPR pairs, get a bit string, and then encode it in a low degree extension, and then respond with, let's say, restriction of that low degree extension to a line.
Okay. So I see. So you think of the string that they get by measuring everything as an encoding of a low degree polynomial of its entire truth table, which they then have to answer consistently with.
That's right. Yep.
Thanks.
Henry, one more. When you say the verifier decides to play these things in the z basis or the x basis, the verifier is classical, the communication is classical. Mm-hmm. What exactly does this mean?
Right. So the verifier will tell the prover, say, now we're playing this low degree test in the z basis. So when they measure their EPR pairs, they should do it in that basis. Or when you tell them to do it in the x basis, they're supposed to do it in the x basis. And the way you check that these are actually different bases is via this magic square game. Okay. And again, I want to point out that the reason that we consider this efficient is because how many EPR pairs are you certifying? 2 to the m. But the time it takes for this verifier to run this test is only polynomial in m. Okay. And so I think one way of looking at this quantum low degree test is that this verifier, it's running in polynomial in m time. It's getting local views of these EPR pairs. And passing this test with high probability is ensuring to the verifier that even though it never sees all 2 to the m measurement results of these EPR pairs, that really there are 2 to the n qubits behind the prover's responses. So the verifier is submitting a poly n bit query, it's getting a poly n bit response. But what's really going on, behind the scenes is that there must be these many, many EPR pairs. The prover is measuring these EPR pairs in some basis that depends on the query they get. They get this huge exponential long string, and they're going to post-process it into this polynomial size response to send back to the verifier. That's the guarantee that the verifier is getting from this interactive proof.
Given that you said that the provers know which of the 3 tests they're getting, I'm confused as to how they could not always just pass the magic square test by setting aside some entangled qubits only for that purpose, and then answering the Z queries and the X queries in some totally unrelated way.
Okay, good. So when I say the magic square test, it's somehow like a magic square game that's embedded into the classical low degree test questions. So they actually don't know, sometimes they don't know if they're playing the magic square test or the classical low degree test. Okay, so in the last couple minutes, I want to get into something slightly different, which is something I call non-commutative property testing. And this is a collection of questions that I think come out of looking at this sort of what's going on really inside this proof of MIP star equals RE and this quantum low degree test. And it seems to suggest some abstract questions in this setting. So let me describe what I mean. So classical property testing, it's a very important subfield of theoretical computer science. And it really emerged after people proved the PCP theorem. And maybe Madhu will correct me if I'm wrong, but I think it's the development of the subject of property testing came hand in hand with the study of probabilistically checkable proofs. And property testing is really about local to global phenomenon in TCS. And the general format of the questions is, if some combinatorial object, maybe it's a graph, maybe it's a Boolean function, suppose that it locally has a property P, some fraction of the time. Does this imply that globally this object has the global property, right? So examples are, is a function a low degree polynomial? If you just look at small local views of a graph and you see that it's planar, does that mean that the graph overall is close to being a planar graph? Or questions like this. So this is in the realm of classical property testing. So in the setting, what you assume is that really you're looking at some fixed ginormous object, right? Maybe it's a graph or function, and it's a fixed object, and you're just getting local views of it, right? So you can think of it as, there's some black box, you plug in some input, and you get an output, and you just want to try to determine what's the structure of this global object inside this black box. Now, let's think about a sort of a new model of property testing. So what if the outputs of this black box are determined by quantum measurements rather than deterministic evaluations? So the inputs and outputs of this box is still classical, but what's going on inside this box might be a quantum measurement of some sort. So in the setting, let's imagine that inside this box, we can model it by saying that there's some dimension n, a Hilbert space that's inside. And for every possible input, there is some associated measurement. And when you put in an input, it will do a measurement inside this box and produce the output. You can also query this box with a sequence of points. But since measurements don't necessarily commute, the distribution of outputs you get might depend on the order in which you query this box. Okay? So one way that you can model it is you can say that the probabilities of the outputs of a sequence of inputs is given by, let's say you multiply the measurement matrices together in some order, and you take the normalized Frobenius norm. Okay. So this is one particular choice, but I think it's a nice choice. So this is the model. And in this model, I think there can be some very clean property testing questions that can be extracted from, let's say, MIP star equals RE, where you don't have to refer to provers or verifiers or entanglement. And as an example, we can take this classical low degree test where you're trying to determine whether a function is consistent with a low degree polynomial. Instead of having a fixed function, you can imagine at every point there's an associated measurement. And let's say that you knew if you took a random line and performed the measurements corresponding to all the points in this line, you get a sequence of values that is consistent with, let's say, univariate polynomial. Then can you conclude that if you took all of the points measurements together, and remember that they don't necessarily all commute, can you say that these are all close to some global measurement that produces a low degree global polynomial? Okay. And in fact, it is true that even though these measurements don't all commute, this classical low degree test forces them to be consistent with a commuting set of measurements. And that's one of the conclusions of this classical low degree test. But there's other questions you can ask. One can imagine non-commutative extensions of graph property testing, where you have a graph, every vertex is associated with a measurement, and you can start to explore if, let's say, you knew that a graph, such a non-commutative graph, was locally k-colorable. Does this mean that all of the points measurements are, in some sense, k-colorable? There's also new questions that aren't just strict generalizations of the classical ones. And let me just end by saying, I think that I think this is a new model of property testing, and there's lots of interesting questions to pursue. And questions can come from both the TCS side as well as the operator algebra side. And there's already things like the low degree test indicate that there's lots of non-trivial things that are going on. And so I think this is an interesting area for exploration. Okay, so this is the very last slide of my talk. Just to summarize, I sort of described a blueprint for verifying the halting problem by recursively composing PCPs. But I think the main bottleneck is, how do you certify that there's enough randomness to check that all these PCPs are correct? And you can certify this randomness by performing very efficient entanglement and randomness tests with this quantum low degree test. And then all of the machinery that goes into analyzing that, I think, is related to this non-commutative property testing. Okay, so with that, thanks. Happy to answer any questions.
Thanks, Henry. That was an absolutely brilliant talk, and about really stunning results. So thanks a lot. Are there any questions?
No questions that have been unanswered so far, but I think if we have a minute or two, if people want to ask.
Yeah, so
maybe can I ask one question? So this verification in your non-commutative testing, right? In other area of math, this is usually related to the Kashtan property, right? I mean, you have few generators and you test on this very few generators, then can something global about the whole group. Is this related here?
Yeah, I was actually planning on asking you the same question.
Okay, so yeah, in principle, the answer in similar situations where I've seen it, the answer is yes. The only problem where one has to be extremely careful is this normalized L2 norm. So there are the differences, right? So they have asked this question under different parameters, and so this normalized L2 norm might change the answer to whether it's exactly Kashtan G property or not. So one has to be, that's a technical detail, one has to be careful.
I see. I mean, the one thing that I know about this Kashtan T property is that it was useful to construct expander graphs. And,
that's true, but it's the same reason. The reason is that you want to know whether a global phenomena holds, and you have few witnesses to do that.
Mm-hmm.
Right? And for instance, in the beginning of our theory, this, beyond quantum embedding, there are these other nice algebras, right? I mean, these hyperfinite algebras, and that's exactly the same. If the algebra is not very nice, then there is a test. Few elements can tell you that something global does not happen, and it's equivalent to one of these definitions. That's sometimes called the spectral gap. So it has a spectral gap and is witnessed by few conditions.
Is there a name to this? A succinct name for
this?
For
Neumann algebras, they call it the spectral gap, period. Yeah. It's a criterion for amenability. So it's in the context of hyperfiniteness amenability.
I don't know if it's okay to, jump in.
Sure.
Because I think people have on the quantum embedding side, right? People have asked whether or not you can have a property T group which is stable, and I think it's that would like the kind of stuff that Henry's talking about with you have something where you do a very efficient check, and then you have that it satisfies a global property that's like stability, right? So it's a very similar type of question to ask if you could get a counterexample to quantum embedding that way. And it's known, at least for the naive type of stability, right, that that I think it's known that they can't be stable, if I'm remembering it correctly, which hopefully I am. So I think it's still an open question if you could see something like property T specifically in the MIP star equals RE proof, but it's there are some obstacles to using property T to do what they've done in the MIP star equals RE proof. So if it just comes down to property T, it's definitely in a non-trivial way.
So it seems like the panel is beckoning to us so strongly that the panelists are already in a conversation. So let me go ahead and start introducing the panel so that we can continue with the conversation, and maybe